In this section, we're going to take a look at the coupling or splitting of signals in an NMR spectrum. So what we find is that a particular signal on the spectrum will actually split due to neighboring protons. Now, just a signal that's unsplit is referred to as a singlet, and it's just a single line. Then it can be split into two lines, which is a doublet, three lines, a triplet, four is a quartet, quintet, sextet, and septet. Typically, once you get over 7 lines, we just refer to that as a multiplet, or M. So the most common type of coupling pattern that you're going to observe is actually from protons that are on adjacent carbon atoms. So if we look at chloroethane, for example, these two carbons are adjacent. Okay, so each carbon has protons attached. So we have this CH2 group on this carbon, on the adjacent carbon, a CH3 group. And these are going to couple because they're on adjacent carbons, or you can also think of them as being separated by 3 bonds. The coupling, at least for simple cases, follows this n+1 rule, where n is the number of protons on the adjacent carbon. So if we want to see what these protons will split into, look at the adjacent carbon, and that carbon has 3 protons. So n equals 3, n+1 equals 4. So the signal for these 2 protons will split into 4 lines, or a quartet. Okay, now if you want to think about it in the opposite direction, of course, this CH3 group, those protons will couple with this CH2 group, but now, since there's 2 protons, n equals 2, so n+1 is going to give us 3. So this methyl group, its signal will split into 3 lines, or a triplet. Okay, now moving over to this next example, the first thing you want to realize is that there is a plane of symmetry that runs through this molecule. So there's only 2 different types of protons. We have proton type A, which is also mirrored on the right side, and then proton type B. So there's only 2 signals on this NMR, but let's first deal with A. So A is coupled to this CH2 group. There's 2 protons here. So with n+1, 2 + 1 gives us 3, or a triplet. Since that triplet corresponds to a total of 4 protons, its integration will be for 4. Okay, now next we can look at proton type B, and it's coupled to this CH2 and this equivalent CH2. So it's coupled to a total of 4 protons. So we do 4 + 1 equals 5. That is a quintet, or sometimes called a pentet. So that will be split into 5 lines, and that will be signal B. And its integration will then just be for 2 hydrogen. So now let's look at an example with an actual NMR spectrum. Here we have this molecule. Here's our first type of proton highlighted in green. Okay, it's separated by these 2 protons by a total of 3 bonds. So that 3 bond splitting is the most common. So now, if we want to first look at this one highlighted in green, okay, on this adjacent carbon there's 2 protons. 2 plus 1 is 3, and that gives us this triplet. Okay, and you can see how the lines do have some symmetry. So our middle line is the tallest, and then we have our other 2 lines symmetrically on the right and left. Now, if we look at the CH2 group highlighted in red, on the adjacent carbon there's only 1 proton. So with n plus 1, we get 1 plus 1, which equals 2. Well, this signal will appear as a doublet. Again, we have a relatively symmetric signal. What you'll find, depending on what textbook you read or who you're talking to, is that coupling or splitting goes by a number of different names. So sometimes you'll hear it referred to as splitting or spin-spin splitting, and that's basically just talking about how a proton is being split due to the neighboring protons. Okay, the next thing you'll sometimes hear it referred to is coupling. And when talking about coupling, we're just saying that one particular type of proton is coupled to another neighboring proton, and this results in the splitting of the signal. And then finally, you'll sometimes hear the term multiplicity, and what this refers to is the type of splitting that is observed. For example, if you have a splitting into 2 lines, the multiplicity is considered a doublet. If the splitting is into 4 lines, the multiplicity is a quartet. So now let's take a look at just some of the basics behind why this signal splitting occurs. And sort of the way to think about this, remember that things in an NMR are affected by the magnetic fields in the environment. So we're going to sort of focus in on this hydrogen highlighted in red. We'll call that HA, and it's coupled to this hydrogen in black, which we'll say is HB. And what the way to think about this is HA, it's B local, so that's its local magnetic field. And it's affected by the magnetic field of proton B. So remember that your NMR instrument, we have our magnet, which provides an external magnetic field. But what happens is we have this proton B affecting the magnetic field of A, but the spin of proton B can either be with the field or it can be against the field. And these would be called, we'll just call them the HB spin states. So effectively, if HB is in the with field spin state, then it's sort of additive to B external. If it's against the field spin state, then it's subtractive from B external. And this subtle difference gives us one line that is a little bit more upfield, one line that is a little bit more downfield, and this gives us our doublet. Okay, now continuing to this next example, again, we're going to focus in on what we'll call HA, but now we have 2 HB protons. So now we have to consider the spin state of both HBs. Here's our external field. So one option is that the spin state of both HB protons are aligned with the field. Another option is that they're both against the field. Okay, but the final options is, let's say this first one is with the field, the second one is against, or it can be the opposite. The second one is against the field, the first one with the field. So probability-wise, we have essentially 2 to 1 to 1, and this gives rise to a triplet. And the triplet has this ratio of the center peak being twice the height of the two external peaks, and that is what gives rise to that signal. And if we do our n+1 rule, we have our 2 plus 1, which gives us our triplet. This next slide just shows us some splitting patterns for some basic groups that you commonly run into in organic chemistry, and just kind of what to look out for on a spectrum to help you identify these groups. And it's really the coupling that helps us peg some of these down. The first one is an ethyl group. So if you have an ethyl group in your molecule, you have a CH2, CH3. The CH2 group will show up as a quartet. The CH3 group, of course, will show up as a triplet. Typically, your quartet is going to show up further downfield, your triplet further upfield. So if you see a quartet and a triplet coupled together, that indicates the presence of an ethyl group in your molecule. Also pay attention to the fact that in order for the two peaks or the two signals in the NMR to be coupled, the line spacing needs to be the same. So the distance between the two peaks in the quartet should be the same as the distance between the two peaks in the triplet. If you can tell visually that there's a large difference, that immediately rules out the fact that those peaks are coupled. The next one is a tert-butyl group, and this is more indicating the absence of coupling. So if you find in your spectrum right around 1 part per million chemical shift, a signal that integrates for 9 hydrogen and it's a singlet, that indicates a tert-butyl group. And because in a tert-butyl group, this carbon doesn't have any hydrogen attached, this signal is not going to be coupled, so therefore we get this singlet integrating for 9 hydrogen. Finally, if you run into an isopropyl group, we have the CH and then 2 equivalent methyl groups. Well, the CH, that is going to appear as a 1 hydrogen integration with a multiplicity of a septet. So that's 7 lines. We have 3 from this hydrogen, 3 from this, 6 plus 1 gives us 7. And then we have a 6 hydrogen integration as a doublet, and that's for these 6 hydrogen and the 2 methyl groups being coupled to this 1 proton and the CH. Now we're going to go through just a few common features of coupling to be aware of when doing these considerations. And the first basically is what we've been talking about. Your most common coupling occurs from protons that are not equivalent and are separated by 3 bonds. So that's why this proton is separated from these 2 protons by a total of 3 bonds, so they're coupled. When this alkene here, we have this proton, and then it's separated from these 3 hydrogen by a total of 3 bonds. And then finally, this is one that seems to get people a lot of times. I think maybe the C double bond O throws you off. But if we start with this hydrogen, count our bonds, we have 1, 2, 3 to get to that hydrogen and this hydrogen. So there's a 3-bond separation. These will be coupled. The aldehyde hydrogen, since there's 2 over here, 2 plus 1 is 3, that will be a triplet. And then the signal for these 2 hydrogen, since there's just 1 proton here, 1 plus 1 is 2, which is a doublet. Okay, the second important feature has to do with another type of coupling, and that is a 2-bond coupling. And 2-bond coupling is observed between protons separated by 2 bonds, but they also must be chemically distinct in order to get this. So here we have an alkene, and these 2 terminal protons on the alkene, they're only separated by 2 bonds, but they are coupled to one another. So they each appear as a doublet. This one is a doublet because it's coupled with this one, and this one is a doublet because it's coupled with the other one. Now the reason they're coupled is because they're chemically distinct. And recall that alkenes sort of lock things in orientation. So we have these bonds locked in position, and what you can think about is this proton is trans to the chlorine, while this proton is cis to the chlorine. So that means these 2 protons are in fact in different chemical environments, and therefore they're chemically distinct and they will couple with one another. Okay, the third thing has to do with protons separated by 4 bonds. Typically, you're not going to observe coupling through a 4-bond separation. So this would be, here we have this methyl group, and the nearest proton is 4 bonds over. There's no coupling here. So this methyl group will show up as a singlet. This CH2 group will also show up as a singlet. The fourth feature has to do with dealing with heteroatoms. So heteroatoms like oxygen and nitrogen commonly connect molecules together, but typically you do not see coupling through these heteroatoms. Even though, so here we have this OH proton, and if we count up our bonds, 1, 2, 3, there's a 3-bond separation between this proton and these protons on the CH2 group. Now we typically see 3-bond separations, but when it comes to going through a heteroatom like an alcohol or a 3-bond separation through a nitrogen, usually that's not observed. So this OH proton, that would show up as a singlet. This CH2 group would show up as a singlet. The same thing for this amine, these 2 nitrogens, they would show up as a singlet, integrating for 2 hydrogen, and this CH2 group, even though it's not coupled through the nitrogen, it is coupled to these 3 protons on the methyl group, so that would show up as a quartet for 2 hydrogen, and then this methyl group is coupled with the CH2, that would be a triplet, integrating for 3 hydrogen. So typically, if you see an alcohol or amine signal in an NMR, it shows up as a singlet, and these signals are often a bit broad. The fifth thing to be aware of, which is something that you've sort of seen as we've gone through these examples, is the fact that chemically equivalent protons do not couple. So in methyl chloride, this CH3 group will show up as a singlet, integrating for 3 hydrogen. These protons are separated from one another by 2 bonds. So if you draw out your CH3, there is a 2-bond separation But the only time we see coupling through a two-bond separation is if these protons were to be chemically distinct. But in the case of just this alkane here, they're chemically equivalent, so you don't get any coupling. The second example, this tends to give people a bit more trouble because you do have a typical three-bond separation. So it's tempting to want to say that this CH2 group would couple with this CH2 group, giving you a triplet. But the thing is, due to symmetry in this molecule, this CH2 is equivalent to this CH2 group. So what happens is there's no coupling between these protons. You get a singlet, and since they're completely equivalent, that singlet is just going to correspond to 4 hydrogen. Let's take a look at this molecule. We'll go through and assign the splitting patterns and then take a look at the spectrum. Well, first we have an alcohol. Alcohol protons typically don't couple, so that will just show up as a singlet. Next we have this CH2 group. Well, that's coupled to the CH2 group on this neighboring carbon. So we have 2 protons here, 2 plus 1 is 3, so this will be a triplet integrating for 2 hydrogen. This next carbon over, well, it's not coupled to anything on the right because there's no protons here, but on the left we have 2 that it's coupled with. 2 plus 1 is 3, so a triplet for 3 hydrogen. Next we have this CH2 group. Well, it's not coupled to anything on the left, but on the right side we have 1 proton here. 1 plus 1 is 2, so that's a doublet for 2 hydrogen. Then this proton, the CH, it's coupled to these 2 CH3 groups. So that is going to show up. We have 3 protons here and 3 here. That's 6 plus 1 is a total of 7. So that will be a septet showing up for a 1 hydrogen integration. And then finally, these methyl groups, they're equivalent, but they are coupled to this CH. So that's just 1. 1 plus 1 is a doublet, but the integration is going to be for 6 hydrogen. Now, if we look at the NMR spectrum, here's our OH singlet. We have this triplet and this triplet. Well, the triplet next to the oxygen is going to be further downfield. So there's that triplet. Here we have this triplet. Now we have our doublet integrating for 2 hydrogen. For our septet integrating for 1 hydrogen. And then our doublet that corresponds to the 6 hydrogen in the 2 methyl groups. The next thing we're going to look at is something called the coupling constant. And what you want to keep in mind is that when you have 2 coupled protons, the signals for each of those will be split in the NMR spectrum, and you can actually calculate a coupling constant for each of those split signals. And what it is basically a measure of the interaction between protons that are coupled. Sometimes you'll hear these referred to as J values, and they're reported in units of Hertz. Here we have chloroethane, and we have this CH2 group is coupled to this CH3 group. Here's our CH2, which is a quartet. Here's our CH3, which shows up as a triplet. Since these protons are coupled, the peak spacing must be identical. So the distance from this first peak to the second peak in the quartet must be the same exact distance as the first peak and the second peak in the triplet. And this distance is the coupling constant. And it's measured in units of hertz. So if we take the peak distance in the quartet and find it to be 8.1 hertz, well, the peak distance in the triplet must also be 8.1 hertz because the two protons are coupled. And this can be really useful if you have a complex spectrum and you're not sure whether two peaks are coupled to one another or not. If you calculate the coupling constants and find that two peaks have identical coupling constants, then you can make a pretty logical assignment as to whether or not protons are coupled. So the way you go about calculating a coupling constant, if you get your computerized spectrum, what's going to happen is every peak in a signal will have its own chemical shift. Also, you'll need to know the frequency of your NMR spectrometer. So for this example, the spectrometer was 300 megahertz. And here we have our chemical shift of every peak in this signal. So what you want to do is pick any two neighboring peaks. Let's just use the first two, and we'll subtract the chemical shift values. So we do 3.482 minus 3.455, and then we multiply this by 300, which is the operating frequency of the spectrometer. So if you do this calculation, you should get 0.27 times 300, which equals 8.1 hertz. So this would be the J value for this particular signal. You can look online or in most textbooks and find some typical coupling constants for coupled protons, and these are pretty standard numbers. So for example, if you have two coupled protons in an alkene that are trans to one another, their coupling constants will typically fall between 12 and 18 hertz. Versus if the two protons are in a cis orientation, the coupling constant will fall between 7 and 12 hertz. So you can see how this could be useful if you need to figure out whether your double bond is cis or trans. You can just look at the coupling constant in the NMR spectrum.